The complex number z equal to 3 plus 4j is written in rectangular form. So this is the real and this is imaginary. And this is the complex number 3 plus 4j. Now if you want to rewrite this rectangular form into polar form, you want to find its amplitude and also the angle, it means the phase. We can apply Pythagorean theory. So the amplitude of this complex number is equal to square root 3 to the power 2 plus 4 to the power 2 and equal to 5. And the angle or the phase is equal to arc tangent 4 over 3, and it is equal to 53.1 degree. Now this complex number can be written now in polar form. Its amplitude is 5 exponential j 53.1 degree. We can now use Euler formula, and this becomes 5 cosine 53.1 degree plus j 5 sine 53.1 degree. If you plug these two numbers into your calculator, you will find this equal to 3 plus 4j. Let's look at this circuit. A AC signal is connected to a resistor and a inductor in series. Now if we measure the voltage across the resistor, we call it VR, and measure the current I, we'll find that these two values, they are in phase. Now it means if I plot, this is the voltage and this is the current, they're in phase. So the peak aligned to the peak, the trough aligned to the trough. And also the peak of the voltage, it means the V, and is proportional to the peak of the current. And the proportional constant, of course, is R, resistance. So this is how the Ohm's law can be applied to the AC circuit. And both the voltage and the current, they are in phase. However, if we look at the voltage across the inductor here, and also measure the current. Now, one important thing is from the Kirchhoff law, this current passing through the inductor is the same phase and the same magnitude as the current passing through the resistor. So these two currents, they are the same. If now we plot the current and the voltage across this inductor, that's what we will find. We can assume the current as a cosine function first. So if this is the current, like a cosine wave, and we'll find the voltage is 90 degree lead the current. It means the cosine curve shift to the left hand side 90 degree. So we can here, now we can imagine like this, and this is here, here, okay. Now the peak of the voltage and the peak of the current, they can be different. Of course, they have different units. However, again, we can say the peak here and the peak here, they are proportional. So we can write down like this: the peak of the voltage across the inductor is proportional to the peak of the current across the inductor. And this time, the proportional constant, we call it XL. So this form is very similar to this. Now, honestly, I think I should write this one as V, the peak of R, equal to R, the I, the peak of R. Of course, this value and these values, they are the same, and also they're in phase. Now, the issue is, what is XL? So XL have the same function as Ohm's law as R. So we can say if R is measured in ohm, the XL should also measure in ohm. So they're the same. But the only thing difference is this time the voltage and the current crossing the inductor, they are 90-degree out of phase. Now, nevertheless, we can write this one in magnitude. So we'll say, if you go through all the theory, the XL, or the magnitude of the XL, is equal to 2 pi FL. So you can see XL has a similar function as R here, but one important thing is the F, it depends on the frequency. It means you can imagine the XL like the resistance, but it depends on frequency. The higher the frequency, the larger than this one. So this is a frequency dependence or resistance, similar function or similar meaning. Okay, now the rest is just plug the number into the definition, of course. So if we plug this number, 2 pi FL, into this equation, 50, and this is 200 times 10 to the minus 3. And you will find this equal to 62.8, and the unit is ohm. Okay. Now, how should we plot this one in our phasor? So first of all, because the voltage across, this is VR, across the resistor, they are in phase. So this is IR. So we can put this one along the horizontal axis. So you can say this is I, and this is VR. Now, in this case, we are better, even better, to just plot the R, because R is along the V and the I. So instead of this one, we can say, okay, we plot the R along the x-axis. So that is what I will do. This is the R here. Now, the inductor, remember the I should be around here, and the voltage of the inductor is 90-degree lead the current. So if we plot the voltage of the inductor should be here, 90-degree lead the current. Again, I don't want to plot the voltage this time. I want to plot the XL. Remember, the voltage is proportional to the current. So I can put the XL along the voltage. So again, this time I plot the XL 90 degree ahead of the resistance, and I remove this one. So this time we use the phasor, just plot the R and the XL. They are both measured in ohm. Next, we want to find what is their sum. So what I mean is, imagine if you have two resistors like this. If you have a DC here and here, R1 and R2. Now you want to ask what is the sum of this R1 and R2. You're saying is I can replace the 2R with 1 here. Now this time of course it's simple. You just equal to R1 plus R2. That's it. But this time you see the XL is 90 degree ahead of the R. So you can say this like a vectors. When you have to add the two vectors, you have to use the rule of vector addition. So to add the two vectors, this one is here. So this one, this time we call the Z. We call this complex impedance. It means it's just like adding the two resistors, but this time one is 90 degree ahead of the other one. And this one, of course, we can do some calculation. Let's do it. So we are doing vector addition this time. So the complex impedance Z is absolute value, or its amplitude, is equal to R square plus XL square. And if you plot this one, 100 square plus 62.8 square, and you will find this is 118.1 degree. Beg your pardon, 118.1 ohm. Again, if you want to find the angle, it means if you want to find this angle here, this is equal to arctangent, and the opposite side is XL, and this is R. It means this is 62.8 over 100, and you will find the angle equal to 32.1 degree. So this is 32.1 degrees. So what is the meaning of this one? The meaning is here. If we look at the time domain, first, the voltage is always along the impedance. Say, for example, if I say what's the voltage of across the resistor R, we'll say this is the voltage across the resistor R, so VR. Now we also know the voltage across the inductor is 90 degree lead. It means now this is the voltage. Now this voltage may or may not be exactly the same, so I assume so this is VR, this is VL. And if you look at the shift here, the difference is 90 degree. So this is VL, this is VR. And here, this 90 degree ahead of the R. How about the Z? The Z is 31 degree ahead of the R. So if now this time we plot another peak here, this is V. This is the source. It means if now we measure the free voltage, the voltage VAC across your source, the voltage across the R, the voltage across the inductor, they're all relative shift from each other, and the shift is depends or given by this complex or phase diagram. I hope this will give you a lot better understanding of how we use the phase diagram and what's the meaning of Z here. Let's plot the R and the XC on the phasor. The R is along the wheel axis or the horizontal axis. This is R, and the capacitor or the voltage across the capacitor is always 90-degree lag behind the current. So this is XC. Okay. Now let's calculate XC with the formula. The formula say XC is magnitude is equal to 1 over 2 pi FC. So we can say this is 1 over 2 pi, and the frequency is 60 this time, and the capacitance is 220 times 10 to the power negative 6, and you will find this one is equal to 12.06 ohm. And remember, R is equal to 47 ohm. So I have to say this time the R is a lot bigger. So if I can redraw this one here and put the R a lot longer. Okay, now we have two impedance. One is R, one is XC, and we want to find the sum. So the sum is vector sum. We have to add them like a vectors. So this is here. We call it Z, complex impedance. And of course, the magnitude of the Z is equal to square root R square plus XC is magnitude square, and this is 47 square plus 12.06 square, and it is equal to 48.5 ohm. Now we also need to find the angle here. The angle is arc tangent, and this one is XC over R. Remember, this is a negative angle, so I have to put the negative in front of the arc tangent. This is negative here, and this will become 12.06 47 minus 14.4 degree. So what it means is, if we think in the time domain t, the R is along or in phase of the current and also the voltage. So this is I, and also this is the voltage across the R. They're all along. So if I plot the I here, so they are cosine, so I put the cosine here. So this is I, the current, the same across the resistor, and also the same across the capacitor. Next, the voltage across the capacitor here, if we measure the voltage VC, which is aligned to the impedance, aligned to the XC. So this is 90 degree lag behind. So this is 90 degree. It means the voltage here should be here. Okay. Here. 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 So this is, if you just look at the phase here is 90 degree, and this is the voltage across the capacitor. Now, how about the AC signal? The AC signal is voltage is not following the voltage across the resistor. It means they are not following, and also not following the voltage across the capacitor. It is circuit in between, and it follows Z, the total impedance. So what I mean is, we can just think of like the sum of two resistors. After you find the sum, you find this one here. So this is like a complex resistor, and this is the voltage here. So the voltage here will follow this one. And what's this one? This is 14 degree. So it means the voltage is roughly not 90 degree. This time is about 14 degree. So this from here to here is roughly 14.4 degree. The negative mean is shift to the right hand side. So this is here. Okay, so this is 14.4 degree. In the phasor, this is this angle here, 14.4 degree. Now, this voltage here, this is VAC, will proportional to the current, the blue one here. This is the current, which is follow the voltage across the resistor. So this proportional here is the VAC, or this time we use root mean square, is proportional to the current, but the current is not in phase. The current is aligned to the resistor. So they have our phase, but still their peak or their root mean square value, they are in proportional. So this one is root mean square, and the proportional constant, this is the Z here. Of course, we are all talking about the magnitude. Okay, so the I root mean square is equal to 50 over, let me double check, 47 square plus 12.06 square root. Yep, 48.5, and it will equal to 1.03 ampere. If the frequency double, it means 2F equal to 2 times 60, 120 Hertz. The amplitude of the complex impedance for the capacitor is equal to 1/4 2 pi FC, and if you plug this one in, this is equal to 6.03 ohm. Now this time is magnitude of the total impedance is square root and 47 square plus 6.03 square, and you will get 47.4 ohm. And now because the complex impedance become less, so the current, or the would mean square value of the current would mean square value, and this is the complex impedance, and this is 50 over 47.4, and you will find 1.05 ampere. Now what I mean is, this is, assume this is the original, and this is R, and this is XC. Okay, now if this is for frequency equal to 60 Hertz, now if the frequency double, the R, it won't change, but XC will reduce half. So this is XC, and therefore the Z here also change, both the amplitude and the angle as well. Let's calculate the angle. Now the new angle phi is equal to minus arctangent, the new and the original. So this one is 6.03, and this is 47. So this is negative 7.3 degree. So yes, the angle also become less. So this is the original, this is the new one. This is the series RL circuit, and the resistance is 68 ohm, and the inductance is 100 millihenry. Now the inductive reactance XL is defined as 2 pi FL. So now if you plug the number, this is 60, and this is 100 times 10 to the minus 3, and you will find this is equal to 37.7 ohms. Now let's plot the inductive reactance on the phasor. First, the resistance R is along the x-axis, and the inductive reactance is 90 degree lead the resistance. So this is here, and this is 68 ohm, and this is 37.7 ohm. XL inductive reactance. Now if you add these two together, so it means now if you just consider the AC source and the AC source, when you combine the resistance and the inductance together, it will have a complex component. Okay, so this is VAC, this is the current. Okay, the current is the same, but this time again, let's find the magnitude of VAC. So this is here. This is Z first is the impedance. So it's the sum of these inductive reactance and the R. It means just like, think about again, if you have a DC circuit, this is the R, and if you have another R, you can reduce this one into your source and one single resistors. And this one is R1 plus R2. This R1, R2. You just add them. We do the same thing. We add R and the inductance. However, they are 90-degree out of phase, so we cannot just add them. We have to use vector addition. So Z here is equal to square root, of course, 68 square plus 37.7 square. And you will find this is equal to 77.8 ohm. So what I mean is, this one, the current will along for sure the R, because they're all in phase. Remember, this is the characteristic of a resistor. The current, the voltage, and the resistance, they're all in phase. They're all along the x-axis. But your source, this time, actually out of phase. So the source is along the complex impedance, and the angle here, and we find this theta, and the theta here is arc tangent, and of course 37.7, 68 ohm, and you will find this is equal to 27, beg your pardon, 29.0 degree is positive, remember. Okay, so if you plot this one like a time domain again, this is what you will see. Okay, so the R or the R, the I, the VR, all these three, the I, the voltage across here, and the resistance, they're all in phase. So I just plot one will be enough. So if I plot this one here, so I can say this is, they're all the same, but this is the current here. So of course you have the peak here as well. So this is the peak. Okay. Next, the XL, the inductive reactance. This will be along in phase of the voltage across the inductor. So it means this is the voltage along the inductor. Now this is 90 degrees ahead. So we'll shift the blue curve to the left 90 degree, and this is, now we don't know how much, we just roughly guess. Okay, so this is 90 degrees shift to the left, so this is the voltage across the inductor, and this is the blue one is the current passing through the resistor. Now, the AC, the source voltage, which is along the complex impedance, so it's a VAC. They must along, and so this angle is what we found 29 degrees. So it's to the left. Okay, so now if we look at the angle, the peak here, And remember, we use the blue as our reference. And this shift here is 29 degrees. And if we look at the peak of this one and the peak of the current, they're proportional to each other. So what I mean is, we can write the same thing. The voltage of the AC source is proportional to the peak of the current. Wow. If you are given in root mean square value, you can use root mean square value. It doesn't matter as long as we know their consistency. And of course, they are in sort of 29 degrees shift to each other in terms of the phase. So this is all magnitude. So therefore, the I root mean square value is the VAC, which is 120 volt root mean square value, and the complex impedance is 77.75 ohm, and you will find this is equal to 1.54 ampere. This question follows number 5. In this case, if the frequency now is half, it means become 30 Hertz. What will happen? So first, the inductive reactance XL is amplitude will become 2 pi FL, and it will be half, 18.85 ohms. And the impedance is equal to vector sum of these two, and it's equal to 68 to the power 2 plus 18.85 to the power 2, and it is equal to 17.56 ohms. The angle, now it becomes arctangent, and this is XL over R, and it becomes positive. Remember, this is positive. This is 18.85, 65, and this is 15.5 degree. And the current root mean square value is V root mean square value over complex impedance, and this is 120 divided by 17.56, and this is equal to 1.70 ampere. So what I mean is, now similar, the R is along the horizontal axis, which is 68 ohm, but this time the XL, the inductive reactance, is only equal to 18.85, and we can say here the complex impedance, the vector sum of these two, Z is equal to 17.56 ohm, and the angle here, phi, is equal to 15.5 degree, and it means now the source, the AC source, if this is the voltage here, and if this is the current I, so they are our phase, and this is 15.5 degree. However, the amplitude still proportional, so the proportional constant is the Z. So the amplitude of the AC therefore is proportional to the current I, and they're both in root mean square value, and the proportional constant is complex impedance. In this circuit, we have a resistor, inductor, and capacitor. They are all connected in series. Now, first, the current will be the same because for the Kirchhoff law, all current along any series circuit will be exactly the same. Now, let's look at the inductive reactance, which is XL. The XL is defined as 2 pi FL, and the capacitive reactance XC is equal to 1 over 2 pi FC. So you can see XL and XC, they act like a resistor, but they are frequency dependent. So when the frequency change, the absolute value or the amplitude of this also change. Now let's plot this one on the phasor. In this case, we want to find a special condition. It means we want to find a specific frequency such that the inductive reactance and the capacitive reactance, they are exactly the same. But remember, the inductive reactance is 90 degrees lead the resistor, and the capacitive reactance is 90 degrees lag from the resistance. So if the magnitude the same, it means they will cancel out each other. Let's draw it. So this is, here I put the resistance along the horizontal axis R, and as usual I put the inductive reactance 90 degrees ahead or lead the reactance, so XL. This time I want to find the frequency such that it is exactly the same, make the magnitude of capacitive reactance XC, but this time it's 90 degree lag from the resistance. So now under this special condition, they cancel out each other, and it means your circuits only have resistance. So let's find out what is the mathematical relationship between all these. So XL equal to XC, 2 pi FL equal to 1 over 2 pi FC. And if you do a bit of algebra, you will find F squared equal to 1 over 4 pi square CL, or F equal to 1 over square root. I can take the 2 pi out, square root CL. Now, this frequency is very special, so we give a name. We call this resonance frequency, FO here. Now, all you need to do now is plug the number into the relationship. So this is 2 pi square root, and this is 47 mil times 40 milli. And now you see this frequency doesn't depend on the R, and if you plug the number in your calculator, you will find this special frequency is 116.1 Hertz. In this case, this is the resonance frequency. Let's look at different cases here. This is the phasor, and let's draw R along the horizontal axis. Remember, XL, inductive reactance, XL equal to 2 pi FL, and capacitive reactance, XC, equal to 1 over 2 pi FC. So let's first look at if the frequency is equal to resonance frequency. In our previous example, it is equal to 116.1 Hertz. In this case, we know the inductive reactance is equal and opposite to the capacitive reactance. That's why they cancel out. The overall impedance is R. Now, let's think about what happens if F is less than the resonant frequency. If F is less than the resonant frequency, it means the inductive reactance will be less. So it means we can say this is inductive reactance. The R remains unchanged, and the capacitive reactance, because it's 1 over 2 pi F, so it will become stronger. So in this case, if we add all the three vectors, if you think like a vectors, that's what you will find. You will put this one somewhere here, and then now you're going to add this one, and this is your Z, and you can see the value of Z will be larger than R. Now, if this time F is bigger than the resonant frequency, so everything reverse, so the inductance XL become dominant and XC become less. Remember, R remains unchanged. So in this case, after you find the difference, this is XL minus XC, and this will be the overall impedance. This time again is larger than R. So if we combine all this information together, we can express something like this. Okay, now if this is our resonant frequency, in this case 116.1 Hertz, and your impedance, I mean, if you plot the y-axis as your impedance, will be minimum, and then when the frequency larger or smaller than this one, the impedance will be bigger. So therefore you will say roughly, we don't know exactly the shape, but it will be like this. This value is R. And in our case, and if you look at here, this 33 ohm. This is the minimum at the resonant frequency. Similar to the DC circuit, in the AC circuit, you can always reduce your circuit into an AC source, and we call this Thevenin AC source. Thevenin. Remember, this is an AC source, and we can reduce all your circuit into a complex impedance. So this is Z, and now you have a load. Now this load itself have two different cases. If the load itself is a complex impedance, it means it contains inductor or capacitor. Let's put the value on our diagram. This is 50 volt with 0° phase shift. The Thevenin impedance ZTH is equal to 5 plus 2J in ohm, of course. Now the question is, what value of this complex impedance of the load you choose such that the maximum power will dissipate on the load. And the theory say it's very easy. All you need to do is choose the complex conjugate of your Thevenin impedance. It means this should be 5 minus 2J ohm. If you can reduce your AC circuit into the Thevenin equivalent AC source and the Thevenin equivalent complex impedance ZTH, in this case, you can want to find what is the maximum power it will get from this circuit. Now, this time, if the load is a pure resistive, it means if this is a resistance RL. Now, the theory say this load, if it is equal to the magnitude of your Thevenin equivalent impedance, and then there will be maximum transfer of the power. It means if this is equal to 5 square plus 2 square ohm, and it means 5.39 ohm, there will be a maximum transfer of power.